Okay, so let's continue our discussion from yesterday. Let me begin by drawing an example or a diagram where we ended. So you would have two horizons. Again, I'm only drawing a portion of it. R plus and the inner horizon R minus. Then you have the infinite redshift surface, and we'll call this R plus infinity. This is a function of theta, and the outer and the inner. I'm not going to write it, but because it's just too cluttered, we have a ring singularity. Yeah, and that is sort of where we ended up yesterday. And so what we will do is we'll probe the various regions of the Kerr geometry that we talked about yesterday and study its properties. I'll begin by why we call this the infinite redshift surface. Let me see if I wanted to label any other portion. Nope, except maybe point out that this is given by R equals 0 and theta equals pi over 2. Kerr geometry, as you know, it is described by two parameters, m and a. We have shown yesterday that m stands for mass, and a, I have alluded that it is an angular momentum quantity. And slowly we'll get clarity on this as well. I should have pointed out that if you look at the Kerr metric in particular in the Boyer-Lindquist coordinates, if you set, this is easily seen in the Boyer-Lindquist coordinates, if you set a equals 0, it reduces to the Schwarzschild metric. Interestingly enough, if you leave a alone and set m equal to 0, this is Minkowski spacetime. So that is curious and perhaps not so well known feature. Okay, so how do we tackle different portions of space-time? I may have mentioned this, but light is our wild card. It's the Lorentz invariant speed, so we will use light to penetrate various regions, and it's used in all sorts of applications. So let me begin by a few approximations that, well, if you're a mathematician, you may not be familiar with the physics portion here, but if you look at an individual photon, a single particle of light, right? Photons travel through null geodesics. And I'll explain what null geodesics are. And so a null geodesic is a curve, right? And this curve has some velocity vector. And maybe I'll call it L for light, and I'll connect that to null. Well, so this is null, which means throughout. If you take the velocity vector, it's the 4 velocity, and if you find the inner product of the 4 velocity with itself, you get 0. This is perhaps a math way of saying it. If you are a physics, particularly an undergraduate student, you will write this as G mu nu, L mu, L nu. Okay? And repeated indices up and down mean summation. Well, that's null. So what is a geodesic? A geodesic satisfies the following equation. L mu, L mu, L nu equal to 0. Okay, this is the usual covariant derivative. Again, written more abstractly, this is equivalent to saying I'm just explaining various notation and tradition of notation. This is just L equal to 0. So it's a curve whose velocity vector satisfies this equation. Okay, right. So did I mention null geodesics, the two standard examples at all last time we met? No, we did not. So it's simply just a calculation to verify the following. There are two standard null geodesic vector fields, as a matter of fact, in Kerr geometry that is very handy, very useful. It has deeper meaning, and perhaps it has to do with the origin of the Kerr geometry as well. But that aside, I'll call one of them L, r squared plus a squared over delta dt plus dr plus a over delta d phi. This, the radial component is positive, so this is outgoing. And it has an infalling cousin as well. Minus dr plus a over delta d phi. This is the infalling. So this is the path a photon, a single photon takes. In particular, well, a null geodesic is a path that a single photon takes. These are two examples of a null geodesic. Okay, so if you have a null geodesic, the energy momentum 4 vector is simply something that is proportional to the null geodesic itself. Okay, it is, let's say we're talking about the outgoing beam of light. So the energy momentum 4 vector, again, maybe we can write it like so, is proportional to L mu. Now this photon, could be blue light, could be green light, so it could have various frequencies, various colors. So for scaling reasons, we can just put some sort of a parameter, and it won't affect what we're doing. I could call it by a clever name, but I can't think of anything. So just by habit, perhaps bad habit, I'm just going to call it E. Okay? So you have a beam of light flowing through this geodesic, and its energy momentum is given by this 4 vector. The other fact that you would need, so let me get rid of n at the moment. So here's a beam of light. Let's say you're standing over here, and you see this beam of light. And gosh, I didn't draw a straight line now, did I? Because you all know that gravitation warps space and time, and light can get bent. Maybe I shouldn't make it so drastic, unless your head is just repelling light. So maybe even a beam of light that is being gently bent, okay? And so you encounter this photon, and you have a 4 velocity. Over here, as you're measuring, you have a 4 velocity u. And the photon has a 4 velocity, or 4 momentum, I should say, p. The energy that you would measure is defined by minus g u p. Again, let's use this analogy to write this more geometrically. Are we good? So the energy of the photon of the photon as measured by an observer with 4 velocity u is given by energy equals minus g u p, or equivalently minus g mu nu u mu p nu. Fine. And I couldn't think of a better way of presenting this, but you should also know that the energy of a photon I just couldn't think of a better way to do this, so here I am presenting it using a little bit of quantum mechanics, guys. This is not a course in quantum mechanics, but you know this from modern physics. If you are a physicist and if you're a mathematician, you know it by definition. Okay? The energy of a single photon, it depends on the color of the photon. It depends on the frequency of light that you observe. The greater the frequency, the larger the energy. Okay? And so, well, this is energy, that's frequency. Well, you can't have cousins that are not of same units, so you must need a constant to balance off the quantity. So this is the Planck, famous Planck constant. So armed with all of this, we're going to penetrate the infinite redshift surface. So let me erase all the crucial information that I just wrote. There are 2 observers, one close to the infinite redshift surface and one far away, perhaps on Earth. And this person close to the infinite redshift surface sends out a photon. Let's call this observer 1, Bob and Alice, if you will, and this observer will be 2. I call it the infinite redshift surface, right? Well, orange is close enough to red, so here is my observer 2. And this person sends off a photon. So energy, every time I put a subscript 1, it refers to this object. That's equal to, well, energy of a photon, it's h, Planck's constant times frequency, 1. And by definition, that is minus g u p. And p is nothing but, oh, let me not worry about this. H nu 1 is E times L from here. That's the photon that was sent. Okay, so and we know this L. So what is U? This is an observer just standing. U. Just not moving at all. So the 4 velocity is proportional just to the time component. This observer is just moving in time, not moving in space at all. Well, U has to be normalized, so minus g t t, located at some r1, because it's observer 1. And we're going to evaluate this at R1, this location here, R1. Okay, so it's going to be, well, thankfully I've left this and that So you will see it is minus this E over delta. U only has T component, but nonetheless, both of this will come into play because the metric has a T phi term. So, and this factor comes out, 1 over minus G minus GTT at R1. And it's R1 squared plus A squared GTT R1 plus A GT phi at R1. Again, this is because U has time component, but so the TT component comes here, and the metric has a T phi component, and that comes here. This is one of the canonical relations in Kerr geometry in Boyer-Lindquist coordinate that I wrote yesterday. And when you put this, if you look at this term, this is equal to minus delta. And so you would get H nu1 is equal to E over a very simple expression, minus GTT at R1. Now the same photon will traverse all the way from close to the black hole to where you are on Earth and reaches point 2. And at point 2, the observer is going to measure the energy. And energy of a photon, as you know, is h nu. It's going to be exactly this, but the space-time point where it's evaluated is some R2. And so you would get this to be, it's the same photon, same E, over minus GTT R2. Yeah? And so if I take H nu2 and H nu1 and divide, I'm going to simply get minus GTT R1 minus GTT R2. Watch this. I'm just going to cancel the H because we're going to observe colors. What's happening to this infinite, what is special about this infinite redshift surface? Well, what's special about this surface is the fact that GTT is, well, as you approach it, but exactly at that location, is 0. So the closer the observer is to the infinite redshift surface, the smaller this quantity is. This goes to 0. In fact, if this observer is actually on the infinite redshift, you don't see the frequency at all. One pulse between the pulse of a wave, there's infinite lapse in time. Yep, and hence this is the infinite redshift surface. And so perhaps if the observer is not close enough, what was blue light, you receive it as a redshifted, reddish, in our case orange light. And that explains the term, the infinite redshift surface. Okay? Good. So that part is now clear. And we can get rid of these observers. Now, there's a lot of good, interesting properties about this region. We will tackle it, but for now, let's just name this region. This is called the ergosphere. to understand the properties of the ergosphere, and there are many, we have to come up with better coordinate system to understand causality. Perhaps there's no immediate need to do that, but there's a law of conservation of difficulty, so we might as well get through that stuff because it becomes very handy. So we're going to use our beam of light, perhaps the infalling geodesic, to penetrate more and more, so much so that we're going to get close to the event horizon, the outer event horizon, and to see what's going on. To see if there's an actual singularity. Remember, the metric is not defined in Boyer-Lindquist coordinates at the horizons. So, let me, just for notation, the space-time, the Kerr space-time in Boyer-Lindquist coordinates following O'Neill, I will refer to as space-time K, so that I can distinguish the various space-times generated by different coordinate transformations because they have different properties. Remember, we talked about block 1. Block 1 is R greater than R plus. Block 2 is R plus, R minus, in the region between the horizon, and block 3 is R less than R plus. And the Boyer-Lindquist coordinates are undefined at R plus and R minus. Okay, so let me talk a little bit about light cones before I do a coordinate transformation. So at any point in space-time, so I'll make it clear that it doesn't, I'm talking about fully, full GR here. It doesn't have to stand perpendicular like it's always drawn. Space-time could be curved, bent, and all sorts. And it might be that the future points this way. I'm going to take two vectors. I'm going to take one time-like vector and one light-like vector, and I'm going to put them in the same cone. Let me take this guy and call it T for time-like. And let me take a vector here and call it L. Because, as you can see, as I've drawn, they're in the same light cone, you know from your GR course that the inner product is less than 0. As a matter of fact, that's how you know that they are in the same light cone. If you have one time-like vector and one light-like vector, you take their inner product. If it's less than 0, they are in the same light cone. Fine. Now suppose you have two light-like vectors. If they are in the same light cone, this happens if and only if, again. The only time the inner product actually becomes 0 in the same light cone is if L1 dot L2 is 0, in which case L1 and L2 is the same vector. Otherwise, if you take two distinct causal vectors in the same light cone, their inner product is 0. This is not hard to see, but let me give you a simple example. Look at special relativity, where T is 1, 0, 0, 0, and L is 1, 1, 0, 0. Yeah? So what is T dot L? anytime like vector can be made 1, 0, 0, 0. So, and same thing is true with light-like vectors. Even if I took L1 to be 1, 1, 0, 0, correct, and L2 to be 1, minus 1, 0, 0. What is L1 dot L2? It is minus 1, minus 1. Am I correct? Minus 2, which is less than 0. So if you have two distinct causal vectors, they belong in the same light cone if their inner product is negative. You can clearly see if I make this minus, this is going to be plus. So that is how you tell if you have a causal vector if something is future pointing or past pointing. That becomes very important in constructing our coordinate system. Okay? So let's look at over here. Which way do you think we want future to point? At least in the Boyer-Lindquist coordinate, if you look at this vector, which is just d dt, we would want this to be future pointing. Okay. Let me take my favorite null vector, r squared plus a squared over delta dt minus dr plus a over delta d phi. What is L dot n? I think we just did it. Or the dot of these two, g of n dt is r squared plus a squared delta gtt plus a over delta gt phi, and this is what? Minus delta from canonical relations again. So it's less than 0. So the fact of the matter is, in Boyer-Lindquist coordinates, so I don't need to say in Boyer-Lindquist coordinates, I can just say in K. Set d dt to be future pointing, as we would want in block 1. We should not be hasty enough to set it future pointing in block 2 because the metric is singular. So then we know n is future pointing in block 1. Did I get notation heavy? Any questions? Just for clarity. Yeah? Good. Why did I make such a big deal about causality? Because we just take it for granted. And you can take it for granted until you penetrate a region where the metric is singular. Because if we're going to unravel this, we have to see which way the light cone tips. You may have heard of, in Schwarzschild, for example, the light cone tips towards the black hole. Well, that is because implicitly you've assumed that you made a black hole transformation. You could make a white hole transformation, and your light cone is going to tip the other way. But which way it tips, we have to be careful, and the tipping point is calculated by using inner products. That'll determine its fate. Okay. So our goal is using light, perhaps, to find a coordinate system where, and this is good because it gives us an on how to actually change coordinate systems. Okay? The infalling Kerr-Child coordinate system. This will be called Kerr K-bar. This will also be the black hole coordinate system, as opposed to the white hole coordinate system. Okay, let me write the two sets. So we have in Boyer-Lindquist coordinates, we're going to transform it. And again, what is trivial and minute, I'm just going to clarify, and I'll make a point as to why I clarified shortly. I'm going to write this T bar, R bar, theta bar, phi bar. It seems overly redundant, but we're going to do it nonetheless. So what is the transformation? Well, let me give it to you in this form. dt bar is defined as dt plus r squared over a squared over delta dr, and d phi bar, d phi plus a over delta dr. This is just the definition. Oddly enough, look at this. This is trivial, right? Oops. Well, that's wrong. This is correct. You might say, why am I putting r bar on r and theta bar on theta if they're exactly the same? And we'll see shortly. The reason is so they're not the same, huh? It is very important to distinguish. So we'll hang on to it. Okay? All right, so now the question is how vectors transform and what does the metric look like. So here it is, dt bar, dr bar. Are we good? Yeah. d phi bar equal to, let me write this as 1g00, and I think again O'Neill may have used the same symbols, so it'll be easy for you to refer to. dt, dr, d theta, d phi, and I'm going to call this matrix A. Well, this is obviously how one forms transform. And listen, you're probably thinking, why am I writing it in this form? That's not how coordinate transformations are given. There are explicit things that can be integrated out. The answer is yes, and we'll see what it integrates to. It's not difficult. So if you want to know what T bar exactly is, it is this. Simple as that, and that is integrable. I could write down the expression, but at this point, this is more illuminating, so I'll just leave it like so. And then, so you know then dx bar mu is equal to, let me look at the components. If you have a vector in the Kerr's child, so I put a bar on it, any vector, well, this is x bar mu, dx nu, and y mu, where this is exactly A. If you want to know how the one forms transform, so this is nothing but the inverse of that. Well, inverse adjoint, because the multiplication happens over here rather than over here. Yeah, transpose, inverse transpose. That's what it is. So in particular, vector fields transform exactly with this matrices.
Write down G and H.
Oh, I didn't tell you what G and H are. You can guess. What is G? Let me write it. So over here, G is, thank you, r squared plus a squared over delta, and H is a over delta. The resulting spacetime, whatever it is, we call k bar. Yeah? Let me do one thing before I show you the metric. Let's look at what L bar is. Oh, actually, let me use N because it's infalling. N bar. Well, that's precisely this matrix. So the first component is going to be 1 times r squared plus a squared over delta. This is the t component. You want me to write it out? It's perhaps not a bad idea. And then r squared plus a squared delta infalling -1, 0, a over delta. Right? Look, this is precisely dt bar over dt is what this is. So this is exactly this matrix. Okay, so let's find out what n bar is equal to. So it's going to be this, that's going to be the first entry. So help me with this. It's going to be r squared plus a squared delta plus minus g in the dt component, and then -1 in the dr component, completely 0, minus h plus a over delta in the d phi component. I don't need this information anymore, but is it clear how we got this before I erase that part of the board? Well, guess what? And I did make a crucial mistake. I did the transformation, but what I did not do was put that. So on the one hand, n is equal to r squared plus a squared over delta dt minus dr plus a over delta d phi. The same vector, when written in Kerr's child coordinate system, looks like that. And hence, recall what I just wrote. Not equal to this is in fact equal to that. So it is important to keep track of bar if you're doing these sort of detailed calculations. Are we good? Okay, so I want to end today's lecture by telling you the main point of why we took the trouble to write this coordinate transformation. If you have a coordinate transformation and patience or access to Maple, are very hardworking freshman students, you can ask them to compute the metric in the new coordinate system. And here it is. The same metric when written in terms of the Kerr's child coordinate system. Let me write it as a matrix. Very good. It looks like this, where z equals 2mr over rho squared. Okay, and then very quickly we can conclude. See, for example, this is GTT. Yeah, this GTR, GT theta, GT phi. Look at this, GRR is 0. Why is that? I just showed you that this guy is a null vector. So the RR inner product is 0. So how do we end a day full of calculations? With a bang, perhaps not a big bang, but nonetheless a bang. Note, the crucial point of today, in K bar, delta equals 0 is not a problem. And that is good news indeed. I don't see a denominator that has delta. We can use this coordinate system to penetrate the event horizon. We can talk about which way is future, which way you can go, and which way you may not turn around. The second point, of course, as expected, as I've hinted, rho squared equals 0 continues to be a problem. And rho squared equals 0 will persist. There's no getting around it. At z too, z has a, there's no getting around this. Yeah? So we have, this is what we have accomplished. We have explained why the infinite redshift surface is called exactly that. We talked about causality and which way future is, and we have done a coordinate system to penetrate this event horizon. Actually, both event horizon. We haven't done causal analysis. We have not yet today, and thus we can easily bang out the next time we meet, is which way is future.